The next paper is Ancient Phases of our Moon, Formation of Lunar Troctolites and Temporal Implications Concerning Crustal Fracturing. And the presenter will be Tabb Prissel, who is talking to us remotely. Hey, Tabb, you're on.
Hey, guys. Can you hear me all right?
Perfect.
Okay, great. So thanks for, I guess, the opportunity to present remotely. I'm sorry that I can't be there with you guys this year. So this is work that I'll be presenting that we published recently last year, 2 papers that I'll be highlighting. My colleagues Jenny Witten, Steve Parman, and Jim Head. And this work was all supported by Survey and then conducted at Brown University during my PhD. But before I get into the topics here, I kind of wanted to first highlight the NASA XMAS program. I had the opportunity to be a science advisor this year. This is a secondary student, so a high school focused program that allows high school students to take a research project and independently move forward with it. So I put up maybe a few bumper lanes, and that was about it. And so I got to work with 3 young ladies that were extraordinary, Karen, Delena, and Pragati. And I hope they were actually at the conference. They won first prize national winners. They were there as part of that prize. And I hope many of you got to talk with them about their project on lunar ice mining. So today, basically kind of 2 points. It doesn't, I'm not sure if that translated well during the email. I have 2 number 1s there. It should be 1 and 2. But they're both very important, so maybe they're both number 1. Anyway, so the take-home messages that I kind of want to highlight, the major points would be that we've done some experimental work that's placed new constraints on the source region of the magnesium suite, and you've heard the importance of kind of this time period of the moon and early evolution. This is around 4.3 billion years old, and so Lars Borg and others have been working on the age dates, and we've been chipping away at some of the compositional constraints that we can place on the source, and also the geologic processes that have taken place during that time. And then the second point we'll hopefully get into here is we did some modeling and calculations of buoyancy-driven magmatic ascent of some of these MG suite melts, and the results contain very suggestive elements about the density and structure state of the ancient lunar crust at the time of MG suite magmatism. So let's see. Can you guys see a figure on the slide?
No.
Okay. So that there's supposed to be a figure. We're missing that. Let's see. Try and share the screen again, maybe here. Essentially, I was going to give a little background here of the MG suite while this is being taken care of. Essentially, just as a reminder, the MG suite is ancient, 4.3 billion years old. Today, I'm going to be primarily focusing on the Troctolites, but the suite of rocks is comprised of Troctolites, pink Spinel Troctolites, Norites, and gabbro-Norites. And essentially, in the Troctolites specifically, these rocks contain the most forstritic olivine among lunar samples, which is very suggestive that the MG suite parent is one of the least fractionated melts of the lunar interior. And so this obviously has great consequences and great implications for kind of these earliest cumulates, mantle cumulates formed during magma ocean differentiation. So let's see if we have the PDF pulled up here now. How does that look? You guys can see? Yeah, great.
Good to go.
So essentially the plot was just a very familiar MG number of the mafic silicates coexisting with the anorthite number of the plagioclase. And then so the, whoops, there we go. I'll be focusing on these guys, the pink Spinel Troctolites, which would be the pink field there, and then the quote-unquote regular Troctolites. And so the last kind of confusing thing about the MG suite is that they contain this creep signature. So they have very primitive major element chemistry and mineralogy, but they also have a highly evolved rare earth or trace element signature. And so thinking about the heterogenesis of these troctolites, I'm going to be discussing two kind of primary competing models. The first is that during this mantle overturn process, there was decompression melting of some of these early ultramafic cumulates, which produced a plagioclase undersaturated magnesium-rich magma. And so this model would then invoke a secondary process to either bring the melt to plagioclase saturation, such as contamination or interaction with the anorthositic crust, and then also interaction with perhaps a creep layer to explain the combination of primitive mineralogy and evolved trace element chemistry. And then more recently, the model was invoked to create sort of a hybridized source region that could have been produced also during mantle overturn, which brought the ultramafic cumulates toward the surface and perhaps hybridized in the solid state or semi-solid state with creep-bearing material and also plagioclase-bearing rocks. And then a partial melt from this source region could produce a melt that would crystallize to form olivine and plagioclase troctolitic lithology with a trace element signature consistent with the collected Apollo samples. So these previous models have focused primarily on the major mineralogy and or the creep component. And so today I'm going to be talking about new constraints that we've put on the source region and the processes involved by looking at an accessory mineral spinel and using that as our petrogenetic indicator. So if we move on here to the formation of the MG Sweetest hole by Spinel, the first thing that you should kind of take away or remember here is that based on the major mineralogy, the olivine compositions are essentially indistinguishable between the quote-unquote pink Spinel troctolites and the regular troctolites. For all intents and purposes, the olivine compositions are very similar. When we look at the Spinel compositions among that same suite, the pink Spinel troctolites and also the regular chromite-bearing troctolites, they're very distinct populations. And so this kind of jumps out at me. So why is the olivine composition essentially the same as well as the plagioclase, but I have two different Spinel compositions? And so we wanted to investigate that experimentally. So we designed a series of experiments testing what happens when a basalt interacts with anorthite and produce a sort of a contaminated melt, and then examine the mineralogy produced in these contaminated melts. And we also synthesized in the laboratory at Brown the melt that would be produced by a hybridized source region. And so the natural data are my circles here, and then the experiments, the triangles here. So what we found is that in both sets of experiments, whether this basalt was contaminated by anorthite or a melt that had plagioclase in a hybridized source region, they all produced pink Spinel, very magnesium rich and chromium poor Spinel. So the first thing to think about here, I guess, is that one, pink Spinel is kind of rare on the moon. So the pink Spinel troctolites are, hold on one sec, are actually quite rare. And so the chromite-bearing troctolites are quite common, and they're actually ubiquitous among mantle-derived igneous lithologies. That goes for Earth, Moon, and Mars. So if current models of the hybridized source region are producing pink Spinel and melt wall rock interaction is producing pink Spinel, why is there so few Spinel, but most of the troctolites are dominated by chromite-bearing things? And so what we found is we did some modeling to investigate what happens if we just remove plagioclase, more and more plagioclase from that melt and have more of a typical mantle-derived melt. And these white dots now are our crystallization models. And I'll draw your attention to the bigger circles, which is a troctolite saturated lithology that contains a Spinel composition signified by these white circles. And so the numbers at the top there represent a normative anorthite content, And so we started at 50% normative anorthite and then started removing anorthite from the bulk composition, normative anorthite, down to 15%. And as you can see, as we do that, we approach into the chromite-bearing troctolite field. And so, again, this suggests that I have two distinct Spinel populations that are essentially produced by a magma that has identical Mg number to explain the overlapping olivine compositions, but varies greatly in normative anorthite content or aluminum content, specifically in the melt. So we found that these results actually support the magma wall rock interaction model more so than the hybridized source. And to be specific, I guess, is that the experimental results indicate that the hybridized source cannot be as rich in plagioclase as previously suggested. Otherwise, the only type of troctolite we should see is pink Spinel troctolite, but in fact, the opposite is true. The pink Spinel troctolites are very rare, and then the chromite-bearing troctolites are much more common. And so we think that the model, this melt rock reaction process happening in the early moon is consistent with the low volume of samples. Aluminum diffusion in silicate melts is very slow, and so the contaminated regions of a dike or a given intrusion might be very volumetrically minor. And as we saw in Carly's talk, and she mentioned that the Spinel outcrops on the moon that we find are volumetrically minor. And so this is actually kind of a consistent model now that we're beginning to understand that the hybridized source region model is not sunk by any means, but that the hybridized source model might contain ultramafic cumulates and creep alone and not have very much plagioclase in it. And if we go on here to the second part, the second major point about the density and structure of the earliest period of the lunar crust, we did a buoyancy-driven magmatic ascent model of the MG sweep melts. Essentially asked the question, most of these samples are igneous, plutonic, and pristine. Well, did the troctolite parent melt ever erupt? And if it did not, what prevented it from erupting? Almost 18% of the lunar surface is covered by Mare basalts and pyroclastic deposits. So what was interesting is when we did the density measurements of predicted MG sweep melt compositions, we found that actually the MG sweep melt, these kind of green diamonds here, are essentially 200 to 300 kilograms per cubic meter less dense than Mare basalts and percritic glasses. And so we have density here on the y-axis and titanium content on the x. And these gray circles represent the Mare basalts and percritic glass densities. And for reference, we have the pre-Grail lower crust density and the upper crust pre-Grail density estimates. And so prior to Grail, it appeared that, based on buoyancy considerations alone, only a small percentage of the Mare basalts or percritic glasses could erupt. And so this is very suggestive that alternative mechanisms are needed to generate the eruption of basaltic, high-density basaltic magmas on the moon. Interestingly, if I were to go back in time prior to Grail and do the same study, it would be very suggestive that MG sweep melts could have erupted anywhere they were formed based on buoyancy alone. As it turns out, Grail has come along and given us great new data based on density of the crust and also associated with potential porosity or crustal fracturing associated with this lower density. And you can see that here in the blue range, and then the average by this dotted line, or dashed horizontal line. So what was interesting or very suggestive about this analysis was that if the Grail instrument is measuring the density or porosity of the lunar crust today, when did that fracturing occur? Remember, the MG sweep is very ancient, 4.3 billion years old or older. And so this has very suggestive elements that the lunar crust was perhaps fractured shortly after solidification. And I don't, if that ties into the SPA forming or impact event or not, but it appears as though what is more robust is that a very low density crust is needed to prevent these magmas from erupting. And moving on here to a map from this paper, 2016, and kind of tying in the early part of the study. So this plagioclase undersaturated melt that we think formed the chromite-bearing troctolites and then later interacted with the anorthositic crust to form pink spinel and pink spinel-bearing troctolites is actually most consistent with a plutonic origin. So that was also a very interesting result of tying the two studies together. And if we go down to the third kind of panel, bottom panel here, we see that the white diamonds are the pink spinel anorthosites that Carly touched on. And the white diamonds are areas that we considered in our study. The smaller gray diamonds are ones that are also locations, but we did not consider in the study as they were covered by Mare basalts, basalt flows. What we found is a kind of a cluster or a concentration in the southern nearside highlands. This is actually the precise location that our pink spinel anorthosite parent melt was predicted to erupt or be close to the surface. And also more recently by Michael Sori and others, they found a bunch of positive Bugay anomalies also identified in this region, which could or could not be buried MG sweep. And the conclusion we draw there is that the Southern Highlands appears to be a very promising region for future exploration, either through remote sensing or future sample return missions that could inform us about ancient volcanic and magmatic activity on the moon. And so kind of just to, I'll leave this slide up here after I go through it. This will be the conclusion slide. So that the experimental constraints inform us about the MG Suite hybridized source region and that it was not as rich in plagioclase-bearing rocks as previously suggested. Otherwise, these melts would form pink spinel troctolites exclusively. So we also think that the plagioclase undersaturated magmas are more consistent with a plutonic origin. And we have also concluded that the buoyancy-driven magmatic ascent models do imply that the lunar crust was fractured sometime shortly after solidification. Or another explanation is needed to provide a low-density crust preventing these melts from erupting onto the surface. And probably some of them did, but most of the samples we've returned are plutonic. And then lastly, just to highlight there, the near side Southern Highlands does appear to be a very promising region for studying the ancient volcanic and magmatic activity of the moon. So I can take any questions you guys have.
Okay, thank you very much, Tabb. It's a real inspiration for all of us to see above your right shoulder the LPSC proceedings volumes in the background there. So we have time
Still
for a question
useful.
or two?
Yeah.
Shwai?
Hi, Tabb. This is Shrai. So, question: Carly has a paper saying there is a spinel exposure at perchloride deposits. So, based on the MCube data I examined, sounds like it's kind of like a combination of pink spinel and chromatic spinel. So, do you expect that, or do you have comments about that?
Yeah, so are you talking about the spinels at sinus astium?
Yes, exactly.
Yeah, okay. So what's interesting about these spinel signatures is that they do display, well, okay, this is where I'll go with it. So I'm less confident that they show specifically a chromite absorption. Now chromite, specifically is referring to iron chromium oxide. So by definition, when I say chromite, I am implying that this is extremely iron rich. And I believe my interpretation of the spectral data is that I do see iron absorptions, or that these spinel at sinus astium are more iron rich than most of the MG spinel that Carly and others have identified thus far. But I'm very skeptical about the chromium abundance of these spinels. And in fact, Williams et al., 2016, they did the laboratory testing of chromium-bearing spinel synthesizing in the lab. It wasn't chromite, mind you, this was chromium-bearing spinel. But they found diagnostic absorption features in the very short wavelength, which can be a little noisy in the N-cube data, but we don't see it in the data. So my suspicion is that we have these pyroclastic deposits and we have pyroclastic samples. And the pyroclastic samples are certainly more iron-rich than we would expect for MG sweep magmatism. And so I think it's more likely that some of these, Mare basalts or pyroclastic magmas or percritic magmas, sorry, were also interacting with the crust early on. And I actually would expect the MG suite to interact more with the crust since they are a little bit older compared with our sample age data that we currently have. And some of these later high titanium magmas or younger high titanium magmas may have also interacted with the crust, but to a lesser extent. So I guess that would be, I'm not sure if I went on a tangent or if I answered or addressed your question, but those are my thoughts.
Yeah, I can show you some spectra because I think I see some chromium absorption at a shorter wavelengths, like around 0.55 micron. Consistent with the lab spectra dated by Williams.
Carly,
Yes.
sorry, did you have a question, Carly? No, okay. David Kring, sorry.
Okay, if I recall correctly, Juliana Gross has a impact melt mixing model for the Spinel. What favors that model or not favors that model as opposed to yours?
Sure. So the results, and I'm actually, I'm at Rutgers right now, and Juliana and I are working on several studies that we're very excited to present for you guys. And one of the issues that she found when she did these experiments, she was testing, synthesizing impact melts, and then letting those impact melts crystallize to see what she got. You produce pink spinel because you're mixing crustal material with mantle material, but you don't produce a lot of it. So for any given magmatic composition, remember that spinel, or for most magmatic compositions, spinel is an accessory mineral. So it's not like olivine and plagioclase that, for one, it can't chemically evolve as much as olivine or plagioclase throughout crystallization. And it's also kind of only stable in a short window of time. And so naturally, when we look at rocks, it shows up in very low modal abundance. So I think by impact process alone, a giant hurdle to explain would be that I have kilometer-sized outcrops on the moon. Now, that's not to say that it can't happen or accumulate through crystal settling into a spinel-rich deposit. But one other thing I would add is that of the work that has been done by Carly Peters and Deepak Dhingra and others, is that they don't appear to be associated with impact melt sheets. They are more consistent with the idea that these things have been excavated from depth and brought to an exposed surface. And I think certainly impacting would give you the heat necessary to mix these things. But I think also one of the studies that Juliana and I are working on is kind of the thermal evolution of the crust in relation to the applicability or the ability of magmas to interact with it. And so I think I'll be looking forward to see the reviews on this study to see if we can really pin down one over the other.
Okay, thank you, Tabb. That's really excellent and good. We look forward to hearing reports on your work from with Juliana as well. Carly, did you say you had a comment? Oh, sorry.